in the today's tutorial, what we are going to cover, we are going to cover bit magic. So in the today's topic, we are going to cover a few topics like power of 2, ones in binary representation of a number, and find single occurring element in an array. So all this can be done using bit magic. So let's get started with the tutorial. So what we can do, we'll start with bit magic, and here first the first program we are going to make is power of 2, is power of 2. So basically what it takes in n as an integer, n as an input, and in the output it returns us a value whether true or false, true or false as an output. If it tells, if it is a power of 2, so where it is going to check if n is a power of 2. So for example, uh, 512, so it will return true since it is a power of 2, because 512 is equal to 2 to the power 9. Okay, so in the same way, for like 1024, it will return true because 1024 is equal to 2 to the power 10. So this double star indicates that it is a power symbol. So we'll try to make this program to define is power of 2, is power of 2, and it takes an integer and as an input. So we are going to define two values: x is equal to n, y is equal to n bitwise and with n minus 1, and then we are going to take the not of this whole value and then return x and y. Since this operation is a constant mathematical operation, we are doing a bitwise AND, so it takes a time complexity of big O of 1. So on average case, it takes a big O of 1, since we are doing a constant operation, because we are not using any recursive, a for loop, while loop, recursive. We are not making a recursive relation of for loop, while loop. So it is a very constant operation. So basically, so all the mathematical operators, bitwise operators, and constant addition, subtractions, if conditions take O of 1 time. So this is an O of 1 time. Then what we are going to do, we are going to take some test cases. T is equal to int input. Now then integer t is equal to int input. We are going to take a while loop for the test cases, while t is equal to t minus 1, and take an integer n is equal to int input, n is equal to int input. Then print, we are going to print is power of 2, is power of 2 n. So I hope this program is complete. So we are going to run the test cases now. Yeah, I'll have a split window here. So I'll take some test cases. I'll take 10 test cases here. 10 test cases. Let me check with base case. 2 to the power 0 is 2 to the power 0 is 1. So this is base case. So yes, it satisfies. 2 to the power 1 is 2. So yes, it is a power 2. Then 2 to the power 2, 4. Yes, it is a power of 2. Let me check our cases. 512. Yes, it is a power of 2. Then 1024. Yes, it is a power of 2. Then let me take 55. No. 20. No. 22. No. 65. 650. 65. No. 9. No. So these were the cases where we saw, yeah, the above numbers were the power of 2. That is 1, 2, 4, 512, 1024. Okay, so these are the base cases. Here you can also add a condition, like if n is greater, uh, sorry, here you can add a condition for a very corner case. If n less than equal to 0, then you can return false, because our corner case was like the basic corner case, that is 2 to the power 0 is the 2 to the power 0 is 1. That was our corner case. So here you can put a condition here. a corner case. This is a corner case you can put, and we can three test cases: 0, false, -1, false, and -2 also false. So here you can see these were the base cases. Sorry, these are very corner cases. You can see that it is a power of true or not. So now, what we are going to cover next? The next we are going to cover define count bits in an integer. So what is it going to define? So let me make an so this function returns number of ones in binary representation of an integer of an n. Uh, sorry. Of int. So binary number of ones in a binary representation of int. So what we can take, like 5, the binary representation is 101. So the output would be answer is equal to 2. Then for 7, the binary representation is 111, then answer is equal to 3. For 5, we can see the binary representation is 101, so answer is equal to 2 because there are two 1 bits, this one here, and this one here. So for 7, we have a 111 as a binary representation, so we have answer is equal to 3. So for this, so count is equal to 0. So while n, so count. So let me create another program. Look, you can have one approach like this. Define. Uh, you can. This is a very brute force approach. So let me show you. Uh, let me show you. Let me show you here. Here. Okay. So we'll have a string s is equal to str bin of n, and we are going to slice it by two indices because I'll show you on the left of the screen. You can see n is equal to 5. For n is equal to 5, I'll define s is equal to bin n. So here you can see now the binary representation here comes as 0b101. So if I want to remove the first two characters, that is 0b, so I'll do s of 2, then I'll get 101. Okay, then I would simply return s dot count 1. So this is a brute force approach. Plus I'll print also print I'll print the number also. This is the number I'm going to print. Okay, so this is where you find that I'll print this s, and here you can see. So this is a time complexity of big O of n, because this count function would be have the upper bound, like you this might so this O of count function takes O of n times, because in implementation you would for every count you have to iterate over the string. So this would take the O of n time complexity, but we are going to do this in the time complexity of log big O of log n. So we are going to do, so this is very simple. We have a count is equal to 0. So basically what we are going to do, in the end we are going to return count. So in the end we are going to return the count, but before that we will going to calculate count. So what we are going to do this, how we are going to do this, then while n count plus equal to 1, and we will change the value of n bitwise and of n minus 1, and we will return the count. So I'll comment this out, and uh, I brute force of n. So brute force count bits, brute force count bits. So this is the function we are going to call, and the next the before and another one after that we are going to call count bits of n. Okay, so yes, we are done with the program. So let me run. Yes, 10 test cases. So here you can see. Okay, let me, I have some issue with the program. N is equal to n bitwise n minus 1. Okay, there's something. Okay, I didn't put a print statement here because I was returning the value, so I had to put the print statement here. I was returning the value, so I had to put a print statement here because the return count, and here I had to put dot format. So, yeah, now it's fine. Okay, I'll run the program again. So like I have 10 test cases. First is 5. So here you can see the binary representation is 101, and I have two 1 bits, and for 7 3 111, so 333, and like 10. So 1010 is the binary representation. So we have two 1 bits with this one and this one. So this so like so what I'm trying to say, tell you that since the both of the functions give the correct answer, but since this is a brute force approach, because this would take a count of this count function would take a big of O(n) for very large numbers, and on the same side this would take O of log n. So let me try some few numbers. 6110 is the binary representation. We have 2 bit sets, and like for a big number 545. So here you can see we have this binary representation, and we have 3 count bits, 111. Okay, so like in this way you can solve for this type of approach. This can be used to solve. And so thank you guys, thank you so much. I'll catch up in the next